This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to the Distinguished Lecturer Webinar Series. My name is Kerry Cosby, and I'm the Chapters Manager at the IEEE Computer Society. I oversee our more than 600 professional and student chapters around the world and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks before we get started. You can ask your questions in the Q&A panel. Dr. Khan will answer as many questions as he can following the presentation. When you're writing your questions, if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded, and the recording will be made available after the webinar. Data streams demonstrate several unique properties that conform to the characteristics of big data. The Computer Society provides communities, events, and various resources for continued learning and exploration within this field. This year alone, over 7,000 articles have been published on data analytics in the Computer Society Digital Library, including the IEEE Transactions on Knowledge and Data Engineering journal, which publishes the latest trends on data engineering aspects of computer science, AI, and related fields. Furthermore, you can connect and grow with other professionals via our technical committees, such as the TC on Data Engineering. More information will be shared after the webinar. You can also learn more at computer.org. In today's webinar, Dr. Latif Khan will examine big stream data analytics and applications. Data streams are continuous flows of data. Examples of data streams include network traffic, sensor data, call center records, and so on. Data streams demonstrate several unique properties that together conform to characteristics of big data, i.e. volume, velocity, variety, and veracity, and add challenges to data stream mining. In this talk, Dr. Khan will present an organized picture on how to handle various data mining machine learning techniques in data streams. In addition, he will present a number of stream classification applications, such as adaptive website fingerprinting, textual stream analytics, political actor identification over textual stream, attack trace classification using good quality similarity metrics, metric learning, and domain adaptation. This research was funded in part by the NSF, NASA, Air Force Office of Scientific Research, AFOSR, NSA, IBM Research, HPE, and Raytheon. I'd like to introduce our speaker. Dr. Latif Khan is a professor in the Computer Science Department at the University of Texas at Dallas, where he's been teaching and conducting research since September 2000. He received his PhD in computer science from the University of Southern California in August of 2000. Dr. Khan is an ACM Distinguished Scientist and received IEEE's Big Data Security Senior Research Award and Fellow of SIRI, Society of Information Reuse and Integration Award. He's received prestigious awards, including the IEEE Technical Achievement Award for Intelligent Security Informatics and IBM Facility Award for Research in 2016. Dr. Khan has published over 300 papers in premier journals. Currently, his research area focuses on big data management and analytics, data mining and its applications over cybersecurity, complex data management, including geospatial data, and multimedia data. His research has been supported by grants from the NSF, NIH, Air Force Office of Scientific Research, DOE, NSA, IBM, and HPE. Dr. Khan, I'd like to pass the floor to you.
Thank you, Kerry, for the detailed introduction. Good morning. For me, it's in the morning, anyways, and thanks for joining. So as Kerry said, my talk will be related to big data stream analytics and its applications. My name is Latif Khan. I'm a professor in computer science department. So in this work is, I've been doing this work for a decade or for at least 5 years. So I will present some of our, I believe, very classical work. I will present it here and show some of the applications of our work. Okay, so outline of my talk. First, I will introduce you what is data stream. I'll focus on single stream first. Then I will talk about multi-stream. More than one stream will be considered. Then I will introduce you for each stream challenges and how we tackle those challenges. And then I will talk about, at the end of my presentation, some of my new work, more specifically in semi-supervised learning, metric learning, those things I will cover in details. Okay, so outline of my talk, as I told you, I want to focus on the stream mining. And these are the students who did most of the work. They did the PhD under me. And many of them are working in academia and industry. They're very successful. Okay, so here, what is data stream? Data stream means data are continuously coming. You can think about sensor network where all the sensor generates humongous amount of data continuous basis. Then in a social media, many of us posting their messages, you can think about these are streaming data also. And network traffic is another example of the streaming data because packets are flowing from one part to another part, from one router to another router. When it comes to the host, you can think about this is a streaming data. So the bottom line of the streaming data is data continuously coming, and our goal is to do the stream analytics that will be useful for the decision making in real time. So bottom line is here, the data are continuously coming in a stream data, and our goal in this talk will focus on the stream analytics. More specifically, first I will talk about the supervised learning in the context of stream. So in this talk, I will focus on the stream classification problem. As you know, that classification is a supervised learning where you need a ground to build a model. So we will have some historical data. From there, we will build the models. Now recall that stream data is different from the traditional data that are continuously coming here. And our goal is to predict the labels of future instances using the model that we built. Now, it will be useful for decision making. That's a classical application of the classification of supervised learning. Now, what is special about the streaming context? The specialty is data are continuously coming and characteristics of data may change. So that will trigger a bunch of problems in the context of stream. So here's an application how the stream classification can be used in real life. So network traffic, as I told you, is a streaming data, is continuously coming. Packets are continuously arriving to the router, and there is a firewall. Firewall blocks unwanted traffic and so on based on the target, based on the source IP or the protocol they use or the port number they target. So now, even the traffic passes the firewall, there is no guarantee that traffic will be always benign. Traffic might be still malicious. So our goal is to identify incoming traffic, whether it's benign or malicious, using some supervised learning. So here we build a classification model that will identify incoming traffic, whether it's a benign or malicious. If it is benign, it will go to the server. If it is malicious, then it will quantify it and do the further analysis. Now, there is a problem. Problem is, as I told you, problem is, let's say you build a model at the beginning of the year in January, and you are using that classification model in February, March, April, and so on to identify the incoming traffic, whether it's benign or malicious. If it is malicious, then you will block it and do further analysis and so on. Now, attacker may not follow the same attack patterns that your model is trained on. Attacker may change their attack pattern. So in that case, this model might be obsolete very soon. In August or in September, October, this model may not perform at all well. In other words, the model may not identify the attack traffic as an attack. It may identify it as a real attack traffic as a benign. So in that case, that will be a disaster scenario. So the bottom line is you need to update this model. Now the question is, how frequently you need to update the model? So there are two possibilities. You can update every 15 minutes or at the end of the day. That's one possibility. When you do the frequent update, then model may perform well, but there is also a danger that when you do the update, you need to provide the ground truth, and providing the ground truth is always expensive. We may not have enough resources human will provide the annotation, or the ground truth. So in that case, frequently update might be costly. And also it will waste your resources because you need to train your machine learning model and so on. Now, if you do not, so this is one extreme, you frequently update, but there is a possibility that there is no, if you so frequently update, there might be no real changes in the classified performance. Still you are updating it. So that's another issue. Or another extreme is we will not update very frequently. We will update, say, every 6 months or at the end of the year. So in that extreme case, we may not be able to catch some of the new types of attacks. So there are two extremes. One extreme is you frequently update. Other extreme is you will not update. Frequently, you will update rarely or very infrequent way. So both extremes have its merits and demerits. So our goal is to develop a novel technique where we can identify in an unsupervised way, this is the right time to update the model. So I will show you later in my presentation how we can figure it out, how we can determine this is the right time to update the model. So this will be done entirely unsupervised way. So I'll talk about that more details when I feel appropriate. I'll describe it. So here, streaming data introduce a bunch of challenges. First challenge is data are continuously coming, what we call it infinite length, and it requires infinite storage. You cannot keep all this raw data in the main memory. You have to keep it on the disk and so on, because main memory or RAM has a limitation. Second challenge is most classical challenge. People already addressed that issue, call it concept drift. Characteristics of data may change over time. Without loss of generality, let's assume we have two-dimensional data points. So this is a positive instance, and this is a negative instance. And this is line will separate positive instance from the negative instance. Now, you from this training data, let's say this is 1,000 instance in week 1. We build a model, and the model will be, in this case, hyperplane or line separates these two-dimensional data points, positive points from the negative points. And then time passes, new data points arrives in week 2. You will use this model for the prediction. We will say above this will be known as a negative instance, below this will be positive instance. Now, characteristics of data are changing, so the decision boundary has been changed. So this is our old decision boundary, and the new decision boundary will be something like this. So in that case, since the characteristics of data are changing, if we do not update the model, so if we use the old models that we trained previously, that will misclassify some of these blue points. So that shows that we need to update the model. And then the third challenge, what we call it concept evaluation on novel class. We are the first in the world who develops this technique or address that issue called novel class detection. And that work was done a couple of years back. So here we have a novel class exists, and we have a training data like this. And from one particular chunk, we have a bunch of positive instance, bunch of negative instance. And we will apply the decision tree, and decision tree will construct the rule like this. If the point falls into this area, then this will be known as a positive instance. If it falls into this area, it will be known as a negative instance. So this is the decision tree. Now some of the test data comes, and that falls into this area. According to this rule, R1 and R2, some of this X that flows to A quadrant will be identified as a positive class, and some of them that fall into D quadrant will be identified as a negative class. So these are the test instance X, and this test instance X should not be a part of the existing class. It should not be labeled as a positive class, or it should not be labeled as a negative class. It should be labeled as a brand new class or emerging class. And we are the first in the world who develops novel techniques in an unsupervised way that can identify that this would be a brand new class or emerging class. So that I'm going to explain next. So again, how the novel class is emerging. So just think about this scenario in the stream setting. X-axis represents the timeline, and y-axis represents the classes. So up to 400 time unit, there are 3 classes, class 1, class 2, class 3. And up to this 400 time unit, we have these 3 classes in the stream. Now after that, so far in the stream, up to 400 time unit, and we see only class 1, class 2, class 3. There is no class 4. And after time unit 4, class 4 instances are coming. So if we train our model at the beginning, we will train our model with the instances class 1, class 2, and class 3. Now, if we try to use that model after time unit 400, in the stream, if the class 4 instances are emerging, then there is a possibility that our model will not be able to recognize class 4 instances as a class 4. It will recognize it as either class 1 or class 2 or class 3 instances. So that's the traditional, when you use traditional machine learning or data mining technique to classify the incoming instances, that will try to identify incoming instances as a part of the existing class. It cannot identify the incoming instance as a novel class or brand new class or emerging class. So there are 2 ways in a stream setting the classification works. One is called incremental learning. You will every time when you do the testing, and when testing is done, when you have a label data or ground truth, you will update the model immediately. So that's an incremental learning. Another approach is called ensemble-based technique. Ensemble-based technique, from the name you should understand that we will keep multiple models. Ensemble-based technique works very well. In the literature, it shows that ensemble-based technique works better than the incremental learning. So in this work, we will talk about the ensemble-based technique. So we will use 3 models and the ensembles. So 3 classifiers will be built in, will keep in the ensemble. So when the test data, first I will show you how the testing works. This is a testing scenario. So when the test data comes in the stream, X is a text data. We want to find a label or do the prediction. So each of this model from the ensemble will come up with a prediction. Here, two of the models from the ensemble side is a positive class, and one of them says a negative class. Therefore, due to the majority ruling, we will say it will be a positive class. Now, how the training is done, in case of ensemble, data will be divided into a number of chunks. So first there are a couple of ways you can do it. But first I will show you our basic approach, then I will tell you the advanced one and overcome these limitations. So we divide the data stream into an equal and fixed size chunk. So just think about first 1,000 instance will form chunk 1, second 1,000 instance will form chunk 2, third 1,000 instance will form chunk 3. And so here, D1, D2, D3, each of this chunk will form a model M1, M2, M3. And ensemble size, I said, is 3. From this 3 chunk, we have a training data or ground truth at the beginning. So we will build a model and put in the ensemble. And now new chunk arrives, and this new chunk has a bunch of test data. So D4 chunk has a bunch of test data. Each of this test data we will take, and ensemble will come up with a prediction using majority rule and complete the prediction. And time passes. We may have some ground truth on the D4 chunk. Once we have a ground truth or label data, we will build a model M4. Now we need to add this model in the ensemble. If we simply add in the ensemble size will grow over time. So we don't want to do that. We want to keep the ensemble size fixed. So how do you do it? So we need to find the worst model here on the ensemble. So M1, M2, M3, in these 3 models, which one is performing worse on the most recent chunk? So we observe M1, M2, M3 among these 3 models on the most recent training chunk, D4, where we have the ground truth. M2 is performing worse. In other words, accuracy of M2 is the lowest with respect to M1 and M3. So therefore, M2 will be thrown away and M4 will be in. So this way we find a replacement for the recent model. And then using this way, we will do the update of the ensemble. And then we have a test data. Our test chunk arrives, D5. We have a bunch of test data points, and ensemble will do the prediction. And then from the D5, we will have an M5 model. So D5 now have a chunk will have a label data. We build a model M5. So now M5 needs to be added. How we do it? We'll need to find a victim or replacement. In this case, M3 is performing worse, so M3 will be thrown away, M5 will be in. So this way we will continue. Now, so this is the traditional way we deal with the try to handle the concept drift to some extent, and try to handle the infinite length issue, because we divide the data into a number of chunks, and at a certain point, we will consider only a few data points in the main memory. From there, we build the model and discard those points. And we continuously update the model ensemble, so that way, since we update the model or ensemble, we can say that our model is sensitive or works better for the due to the concept drift case. In case of concept drift, our model will do well. As I told you, nobody has done the novel class detection. We are the first who handles this. So let me tell you, let me explain the third challenge, how we do it. This method is non-parametric. There are 3 steps. And first steps is at the training time, and the second and third steps will be at the testing time. So second and third steps will be used for the novel class detection purpose. And first steps will try to determine the decision boundary at the finer grain. The way traditional method works, in the case of decision tree, they construct the decision boundary at the coarser grain. And we will try to build the decision boundary at the finer grain using clustering approach. And then once we do the testing, we'll try to determine whether the novel class forms an outlier or not. If it is an outlier, then we do further check. So let me explain those steps in details. The first steps. So before going to explain the steps, let me tell you. Okay, so we have a last label chunk. We do the training. Basically, some sort of training. In this case, we will do the clustering and build a new model. And once we have the new model, we have to do an update in the ensembles. We can keep only T models in this case, M1, M2, MT models. So we will find a victim and replace with a new model will be in, and the worst model will be out, will be discarded. And then how do we do the testing? So testing case, first the unlabeled test instances arrives. So first we try to determine the outliers. If it is an outlier, then we will buffer it and do the, if it is not an outlier, then it will be a part of the existing class. If it is an outlier, then we will buffer it and try to determine novel class. So I will explain those in details in a minute. So I said there are three steps. The first steps, we try to create the decision boundary at the finer grain. So here I will explain how we create the decision boundary at the finer grain. So let's say this is one particular chunk or 1 week of training data we have. And if we use the decision tree, it will construct the rule like this, A, B, C, D. 4 quadrants. And then, so we'll form the raw training data, and the clusters will be created. Okay, so here I'm trying to say we have some, let's say in this chunk we have 1,000 training data points, and 400 falls into this quadrant, 400 falls into this quadrant, 100 falls into here, and 100 falls into here. So total is 1,000 instances. Now I want to build 100 clusters. So proportionately 40 clusters will be built here, 40 will be built here, let's say, and 10 will be built here, 10 will be built here. So once we have this 100 clusters, each clusters we will keep the cluster centroid, radius, and some other statistical information, and we will discard all the raw data points. So that way we create finer grain decision boundary, and we call those clusters as a pseudo points. Now, there are many ways you can build these clusters. So we use a k-means clustering algorithm, but with a modified version. We basically is a semi-supervised some sort of clustering. So use a traditional clustering. The idea here is the point should be assigned to the closest clusters or centroid. The inter-cluster distance should be intra-cluster distance should be minimized. That's the objective function we use in the traditional k-means. But here we also take into consideration some of the ground truth or label data. So when we build the clusters, we not only take into consideration the unsupervised, where the distance or closeness or proximity, we also take into consideration the cluster ground truth or the label. If the points has a, say, 10 label data points, and 8 of them come from positive class, and 2 of them will come from the negative class in this cluster, in that case, the impurity will be 20%. So we want to build the clusters with the highest purity as possible. So in this objective function, we not only consider the distance, we try to minimize the impurity also. And this objective function, we try to minimize it with the help of EM. And this paper was published in IEEE ICDM conference a couple of, at least 10 years back. Okay, so once we have this finer grained decision boundary from the training data, now test data, now we'll talk about how the testing is done, how we determine the novel class. So when the test data arrives, this is one particular models. So we have T number of models in the ensemble, and this is one of the model. In this model, we keep track of the bunch of clusters, and each cluster's centroid and radius information and so on. Now you can see X, this X, let's say this is one test scenario. And this test, in a sense, inside the decision boundary, you will calculate the distance between X and this cluster centroid, and that distance is smaller than the radius. Therefore, this will be known as is not an outlier, it will be a part of the existing class. On the other hand, this X is not covered by any of the training instance clusters. So therefore, this X will be known as a raw outlier. Raw outlier. And now, if I have a T number of models in this approach, if all the models say X is a raw outlier, then we will feel confident that this might be a potential candidate for the novel class. We call it filter outlier. So basically, this raw outlier may happen due to various reasons. It can happen due to the noise, due to the concept drift, or due to the novel class case. Our goal is to detect this X as a novel class. So that's why we need to do additional check. All of them need to say, in this case, is a raw outlier, then we call it filter outlier, but still we buffer it and check, do a further check. If one of them says not an outlier, then it will be identified in this work as an existing class. So once we have a raw outlier, then we need to buffer it and determine whether this outlier points or filter outliers will form a brand new class or emerging class. So the idea here is when a novel class instances are emerging in the stream, that will not emerge as a single instance. A bunch of test instances will be close together, and they will form outliers, and they will be close together. They will be far away from the existing classes clusters. If we have this property, then we can say that this incoming test stream will form a brand new class or emerging class. So how we can translate that? For this, we use the silhouette coefficient. For silhouette coefficient is a property where you can determine the quality of the clusters. So we do some slight modification for our case. So just think about this. All this black dot represents filter outliers, and we want to determine in one particular model or ensemble, we want to determine whether this filter outliers forms a brand new class or not. So what we will do, the goal here is to we want to see whether this filter outlier points are close among themselves, and at the same time, this filter outlier point should be far away from the existing class instances. In that case, it should be far away from the positive class and negative class. So that will be modeled using the silhouette coefficient. So here, if this silhouette coefficient is greater than 0, that tells you that this particular point X is close to other outlier points, and at the same time, it is far away from the positive class and the negative class, which are the existing classes. So therefore, this X will be a potential novel class. So if you have a Q number of these points like this, so as I told you, we compute the Q nearest neighborhood silhouette coefficient. And if we have at least Q points like this, then we can say that this will form a brand new class or emerging class. So that's the very basic idea for novel class detection. So now there is an issue here. The issue is we divide the data into a number of chunks. So let's say this is a 5,000 instance will form chunk 1, second 5,000 instance will form chunk 2, third 5,000 instance will form chunk 3, and so on. Now the problem is here we try to say, let's say after in third chunk, after 100 instances, there is a concept drift happen, or so characteristics of data have been changed. So in that case, the old model may not perform well. So what do we have to do? So if we need to update the model, but we are updating the model at this point, after the 5,000 instance, at the end of the chunk. So in that case, the concept drift happen after 100 instances. So we have to wait 4,900 instances pass by. After that, we'll update the model. So in that case, those 4,900 instances many of them will be mislabeled or misclassified. So the bottom line is, if you set the chunk size too large, then we may not be able to respond quickly. So that demonstrates this problem. On the other hand, if we set the chunk size too small, then what will be the problem? Let's say our chunk size is 10. So every 10 instances pass by, we will ask the human to provide the ground truth. We will build the model and update the model or ensemble. So the problem is, there is a possibility that there is no concept drift, but still we are updating the model. In that case, we are wasting the resources. So we want to avoid that scenarios also. So we don't want to wait too long. We don't want to do too quickly either. So what is the solution? Solution is it possible we can on the fly determine that somehow we can determine this is the right time to update the model. And in that case, the window size will not be fixed anymore. Some cases window size will be small, some cases window size will be large, and so on. So here is the idea. The idea here is when there is a characteristics of data are changing, and our goal is to immediately identify that scenario and correct our model. So how we can do it? Adapting chunk size. There are existing work before us, what they call it, monitor the error of the classifier or the ensemble. So they see, when they do the prediction, they immediately estimate the error of the models or the ensembles. If the model makes too many errors, then they say the model is not performing well, let's drop this model or update the model. Now the problem is, how do you estimate the error? It's a fully supervised model, because you need to, every time you do the prediction, human needs to provide the ground truth. Then only you can estimate the error, which is not a realistic scenario in a big data stream case. It's not a feasible solution, because the human is very slow to provide the ground truth and is very expensive. So basically the point I'm trying to make, this model is fully supervised, which may not scale well in real life. So we're looking for alternative solution where we will set the chunk size dynamically, but in an unsupervised way. Instead of a fully supervised way, we will develop a technique in an unsupervised way. So how do you do it? The idea here is, we will have at the beginning, we'll have a window, small window, and then in that window, we will see that the model will come up with the prediction. And when the model will come up with the prediction, we will estimate the classifier confidence. So in other words, just think about this. The test data point is arriving, and the ensemble will do the prediction. When ensemble will do the prediction, it will have a confidence values. So confidence means the ensemble will say that it belongs to a positive class with 80% confidence. It belongs to the negative class with, for another instance, it belongs to the negative class with 30% confidence, something like this. So now in this window, we have total, let's say, n number of points. And among these n points, each of them will have a confidence values, classifier confidence when they do the prediction. And then we will try to determine whether the classifier confidence drops, whether the classifier confidence drops over time or not. If it does not drop over time, then we were happy. We will continue with the current window. Basically, we'll increase the window and continue with the current model. If the classifier confidence drops, then what will happen? If we see that the classifier confidence drops significantly over time, then we will update the model and reset the window size. So what we do in order to determine whether there is a significant change happens in the classifier confidence or not, we apply some change point detection algorithm. So here the algorithm will take, for n test points, we will have n in the window, we have n test points, and each of these test points will have the classifier confidence, and we will try to determine at kth point if there is a change happens in the distributions or not. Distribution before k, distribution after k, we try to determine there's any significant change happens or not. If there's any significant change happens between these two distributions, then we can say that the model is not doing well. So basically, we apply change point detection algorithm here to do this. And intuitively, just think about this diagram, the last one. The y-axis represents probability density function, x-axis represents the confidence values. And if we are happy with the current model in the window, then you will see that a classifier will comes up with a prediction with a very high confidence values. So these are the very high. Okay, so we will, this blue line will show you that in the window, classifier will come up with a prediction with a very high confidence values. Those high confidence value will be the prevalent in the window. But when there is a classifier is not doing well, in that case, our model needs to be updated. Classifier will come up with a prediction, and then confidence value will drop significantly. So the probability density function will be something follow this pattern. So in that case, you can say in the window, the confidence values will have a lower values in many cases. So that we try to model it using beta distribution, and we apply the change point detection algorithm here. Okay, now I want to tell you a little bit about the summary of our data set. So first two are synthetic data set, and this two are the packets. We capture network traffic, and we also capture the system calls, and 28 classes, and these are high dimensional data points. And these are the UCI data set we use. These are the three, and converted into a stream. And we reported the results in terms of the false positive, false negative, and the total error rate. Lower the number is better. False positive means existing class will be identified as a novel class. False negative means a novel class instance will be labeled as an existing class. So that's a false negative. And for each of this case, our most recent approach performs better than the traditional approach, and so on. Now, this is the first part of my talk. So do you have any question? If there is no question at this point, I can proceed to the next level. Gary, is there any question in the chat?
There are not any questions at the moment.
That's fine. Is there any pointer I can use? No pointer,
No,
right?
there's not.
Okay, that's fine. Okay, so now I want to show you some of the applications of our work, website fingerprinting in detail. So this work was 3-4 years back. So here, but here the traffic fingerprinting is a type of traffic analysis attack that threatens web navigation privacy. Traffic fingerprinting allows adversaries to learn information about the website accessed by the users by recording patterns in the by recognizing patterns in traffic. So the bottom line here is just think about this applications on the right hand side the figure. User wants to access certain website, and user is very smart. He wants to use the Tor network, which is a so that adversary, even they intercept the traffic, they cannot get the content because it's encrypted. So in that case, goal here as an attacker perspective, attacker wants to know what website client is accessing or user is accessing. And this can be used in good ways or bad ways. Good ways means you want to identify the bad people, bad citizen, then you can use these tools to identify if a particular user access certain terrorist website, you want to identify it using this tool, you can do it. But it can be used bad ways also. If the government is an authoritarian government, then they can prosecute their citizen. So here, so as an attacker, we can only see the encrypted traffic. So is traditional traffic analysis or the technique cannot be used here. So we developed some novel technique where we can extract some additional features. So as an attacker, we can only see the packet length and the time for the to traverse from one point to another point, and the traffic or the packets. So that information we have. From there, we build additional features, and we train our machine learning model. And when in case of test, we try to determine whether client is accessing a certain number of website or not. In the World Wide Web, we have many web pages. We cannot model all of them. We target only few websites. And basically, what we call it monitored versus non-monitored website. So how this work is useful in case of stream? Now the problem is once you build the model, it is possible that website content may be changed. So if the content is changing frequently, then we need to update the model frequently. If we do not update the model frequently, model will not perform well. So the left-hand side, the figure number 9 or 4, where that diagram, adaptive learning. And so y-axis shows the accuracy and x-axis shows the timeline. So if we do not update the model continuous basis, model will be obsolete over time. And on the other hand, when you update the model, we show that basically the model can do better. So that is the reason here why we are showing it. So here that demonstrate that stream mining is very useful work here. Okay, now I want to talk about some of the multi-stream work. This is our most recent work, and these are the people who graduated and working in various companies in the world. Google, Amazon, and Facebook, they are working now. So what I am doing now here, so far I focus on a single stream where we have only one stream. Now I want to talk about multi-stream. So we have a source stream and the target stream. Source stream will have a label data. From there, we build the model. When the target stream arrives, we want to use this the train model from the source stream. We have a label data. From there, we create a training data and we build a model. And that model will be used to test the target streaming data. And now the problem is there might be concept drift may happen. And concept drift, as I told you, may happen in the source stream and the target stream in an asynchronous manner. So be aware of this. And in this multi-stream setting, we assume that source stream will have the label data and target stream doesn't have a label data. Source stream will be used to train the model, and using the source stream or source model, we will do the prediction in the target stream. And concept drift may happen in an asynchronous manner. It can happen in the source stream, and it can happen in the target stream at any point in an asynchronous manner. There is no synchronization. So concept drift needs to be tackled in a wiser way. How this work will be useful, just think about this. Some of the applications. So you have some Amazon data. You have a positive sentiment, negative sentiment about the music review stream. You have a level data there. And using that stream, you will build the models. And when the movie review comes, we don't have a level data in that stream. We want to predict the sentiment of the reviews. So we will use this source stream model to do the prediction in the target stream. That's one application. And then another application can be image has been trained in a black and white scenario. So we have 10 classes, digit classes, 0 class, 1 class, 9 class. And then when you train the model and test it in the target stream where we have a colorful image and so on, a different setting or environment. And in security domain, it will be more challenging. Let's say we have a Windows system called traces data. So there we have a system called traces, and we have a benign data and the malicious or attack data. And these are the ground truth or label we have. And using that, we build a model in the source stream and then test it on the Linux environment. So here, we use the Linux data to build the model. So we have the level or the ground truth in the Linux environment. And from there, we build the model, and then we want to test it on the Windows environment. But there are several challenges. Source and target domains, data dimension may vary. So feature space may not be homogeneous. So in the Windows environment, we may have some system call which is entirely different from the Linux environment system call. So there is no one-to-one mapping, or some features may be entirely customized for each of this environment or OS. So that we need to deal with that, and the distribution may differ. So here what we do the domain adaptation type of work in a multi-stream setting. So domain A and domain B. So domain A, you can think about source stream where we have a level data or ground truth, and domain B, we have only the target stream, we don't have a ground truth. So the idea here is we map these two domains into a latent space, or project of source and target data to a latent feature space. And then in that feature space, with this domain A or the source domains or source streams, ground truth will be used to train the model. And then domain B's will be transformed in, or the target stream will be transformed into this latent space, and then will be used for the prediction. And keep in mind that concept drift may happen in this stream at any time. So here what we did, so we have a source stream and the target stream, S and T, and then the representation is BS and BT. These are the source domain and the target domain. And then we do a projection, WS and W2. Then we map into the latent space, LS and LT, basically common feature space. And then we build the model using a source stream LS in the latent space, and then the ground truth in the YS, which comes from the source. And then we have data coming from the source or target. We read this data, and then first we do the concept drift detection in one of the stream. If there's a concept drift going on, then we will update the model. So same way what we did in initialization phase. If there is no concept drift, then we will continue with the prediction. So this way the algorithm continues. So overall objective function will be like this. So the loss of the BS to LS, latent space, BT to the target, and then this additional penalty function. So this is the main loss. plus the regularization or the penalty terms, we will use it, and we try to minimize this. And for concept drift detection, we use maximum min discrepancy. And we tested it on a number of data set. So the APT is a more some cybersecurity data, some sort of APT attack. And we train it. We have a training data in the Windows environment. Then a system call traces, we have a system call in the Linux environment. You can see the number of features entirely different. For Windows, we have 28 features and 105 in the Linux environment. And dark web to monitor the emergent trends of contraband commerce on the dark web. And these are the data set we use. And Amazon reviews synthetic data we use. And then here we train it. The source stream is Windows and tested in the Linux environment. And you can see these are the baselines. So lower the number is better. The error rate will be reported. So this is our method with the and the support vector. And you can see our model is doing better. And then last but not least, I want to tell you a little bit about our new work, 2 years old work, which is online self-adaptive metric learning on the fly. So just think about this. These are the three images. What do you think about these three images? These two are SUV and this is a sedan car. But if you represent them in original feature space, you will see that probably these two are closer and these two are far away. Although they represent semantically, these two are similar and this is different from these two. So goal here So what I told you, in an original feature space, if you show them, you will see that these two images are close, and this is entirely different from here. But in the semantically, these two should be the same. So we want to learn a metric learning or distance learning or a latent space we want to learn, where these two images will be in that latent space. These two images will be close together, and these images will be far away. So that distance on metric learning, we want to do it. So how we do it? There in real life, there are a lot of ground truth we have. So we will we have anchor points, and with respect to anchor points, we have a positive class with the same class of the anchor points, and we have a negative class. So that way we generate the triplets, and then from the triplet we will build a model. This triplet will serve as a training data, and we'll build a model. And time passes, we may have more triplets, then we will update the model. So that's more the streaming fashion. Okay, so here, so let me explain that model a little bit. So we have a bunch of triplets in the training process, and we keep ensemble again, n number of ensemble models we'll keep in the ensemble, and each of the model will have a weight or the contribution, and we'll aggregate, and it will be used for the image classification, face verification, and image retrieval. So now let's talk about the models a little bit more details. So here, I said, this is a neural network-based model. So we have a anchor points, and we have a positive class and negative class images. So this will form a triplet, and that will be fed into this network. So at the beginning, we have a first one is the linear layer, and we just do each images will be fed there, and then we will calculate the loss and so on. And then here we use the linear, and then we have embedding layer, and so on. So that way we'll build, so each of this will serve as a model. So we have total n number of models. So in this case, L will be 4. So then, so now when you fed into the network, so there is a forward and the backward propagation will update the loss function. So what we do, the idea here is anchor with respect to anchor points. If the point belongs to the same class, then those class points should be close together, should be less than some threshold. And if the points, if a point or an image which is not a part of the anchor class, basically it's a different class. So in that case, that distance should be higher than some threshold. So that type of thing we try to learn here. And since I don't have time, I don't want to talk about those details, but we do the error the estimate and using back propagation to update the weight. And we tested it on a number of data set. So there are 3 tasks we tried in this case, metric learning. So we try to learn that distance function where in the latent space, the same class points will be close together and different class points will be far away. And we tested on 3 tasks. One is the image classification. The second one is the face verification. Third one is the image retrieval. And these are the data set we use, the number of features, number of classes. And our method is the last row. And you can see error rate is the lowest in our case. And then face verification case, we have the similar result, ROC. And this diagram tells you some of the weakness and the strength of our model. So for example, so face verification, we want to know whether the same person or not. In our metric learning, we're able to determine this to represent the same class, and these 2 images represent different different persons. So we are able to do it successfully. But some cases our method also fails. So for example, if I have an image, and if we try to, our case, we predict these are the different person the model predicts, but actually, in fact, they are the same person. So some cases it fails also. And then, so these are the image retrieval based on a query. We will find the similar images, and our method performs there also very well. And then we tested on the cybersecurity data set, and we show effectively that our model works very efficient way. Model does a better prediction. So, and then last but not least, I want to tell you some of our very recent work, what we call it semi-supervised learning. So we have some labeled data, and we have a lot of unlabeled data. From there, we build a model. And so there we use, the idea here is, so we have a bunch of images, and those images may have the label. From there, we create artificial examples or do the image augmentation. And then augmented images now will be fed into the network. And we have 2 components. One is the consistency regularization, which works in a supervised way, and multi-contrastive learning, which is nothing but a distance learning or metric learning. So there we consider these 2, labeled data, unlabeled data, and the data augmented views will be used to do the to learn the better representation, and then we do it for the prediction. We tested it on a image classification domain. We also tested it on the COVID-19 X-ray images and CT scan images, and we show that our method works very well. Finally, we tested it on the chemistry, in a chemistry, some of the chemical images. We try to test it, and we show that with the limited label data, we perform as good as the supervised learning. And that paper was published in a journal, and there's a Nobel laureate from Northwestern was involved in this work. So what I showed you so far I showed you that novel class identification method in the stream is a very powerful method, and I showed you some of the applications, and I extend the work in a multi-stream setting. Then open source big data infrastructure tools for that. I did not cover it here, but and then next focus of my research, I'm doing some federated learning nowadays, and also trying to do some fairness of the stream mining work. And I do also a lot of work in the social good, healthcare, and cybersecurity domain. And if you're interested about our tools, so you can find it here. For a stream classification tool is here in the GitHub. You can download and compare our approach and use it for it. And we have a pattern also that might be, if any company is interested, please let us know. And then multi-stream GitHub code is here. So these are the things we have. And I concluded my talk here, and I appreciate IEEE for giving me the opportunity to present my work here. Thank you. Thank you.
All right, thanks a lot. It's a great presentation. We've got some questions that are currently in the Q&A. If you guys who are out there would like to ask some more questions, feel free to put those in. Let me go with the first question here. It's a fairly involved question, so I'm going to read it. Your comments are appreciated on the subject of documentation and post-classification review. Revising the model means that statistical information from previous model iterations may not be on the same basis as success iterations. It seems that one must store all data and do a reclassification based upon a consistent model. Problematic when discussing law enforcement context, which must be present evidence in legal proceedings. I think they just want to get your sense on this.
Yeah, that's a very valid concern. So for the law enforcement, they cannot discard the raw data. So in our model, we showed that we can discard raw data, but here we are discarding raw data from the main memory. But if you, I assume that if you have a sensitive data and you need to keep it due to the to enforce law, and if you work in the law enforcement area, in that case, it is better not. You can move the data from the main memory to the disk and keep it there. Nowadays, disk is cheap, so it's not an issue. The assumption I said, you cannot keep the raw data in the main memory, but you can still keep the raw data in the disk. So in that case, I don't think it's an issue to apply our technique in case of not only in cybersecurity, it can be applied in other domains, like in law enforcement domain and in the criminal systems domain and so on. So it can be used. It can be used. There is no issue, because the assumption is when you keep the model, you will keep the model in the main memory, but still you will keep the raw data in the disk. Since you are not entirely removing the raw data from the disk, so there's not an issue. You can, when you need it, and on demand basis, you can fetch it.
Okay, that's a great answer. The next question is classification versus regression. Which class of methods suits best stream data analytics?
So here I haven't showed you any regression in a multi-stream setting. Mostly I focus on the classification. Classification means here we try to do the binary classification or multi-class classification, predicting the class levels. Either, say, in the political news, you can think about whether it belongs to a entertainment news, whether it belongs to a political news, whether it belongs to a financial news, something like this. And a regression means, in this case, you can think about, let's say I want to predict the today's Apple stock. I may use the old data, Apple's old performance data, and from there we will build a model. There is some classical work, and you can think about it as a time series data and do the prediction. So a regression problem, we try to address it in a slightly different setting in our case. For example, we want to predict the flight delay. And flight delay may be controlled by the various factors, whether then it will be controlled by the type of the airport and the type of the plane, and those are the issues. So in our model, we want to predict the flight delay, and delay is not a label. It will be a continuous number. It can be 10-minute delay. It can be 5-minute delay for a particular flight. We want to predict. And we show in a stream setting, it works. Our method works also very well. And we have a paper I forgot, 2-3 years back on the multi-stream setting. We call it regression problem. So we train it using, say, United Airlines flight data, train the model. That's a source stream. And then test it on say, for example, an American Airlines flight delay on the test case, or the test stream or the target stream was American Airlines flight. So for the training, we use United Airlines flight delay data and test it on the American Airlines flight data set. So we show that the method works reasonably well in case of regression also.
Okay, that's a great answer. It looks like we've gotten to the end of our questions, and we've gone over our time. So I'd like to take this moment to thank Dr. Khan for his presentation. I'd also like to thank all of you for attending. Our next webinar will be in the series of History of Computing, and that'll be Armenia syncing up with the world CS community and building a new heritage of computer science and engineering. That'll be on November 5th at 7 a.m. U.S. Eastern Time. We'll have our next Build Your Career webinar series webinar on the 18th of November, and that will be a presentation on persuasive conversations, why low-impact words don't work, and that's by Elsa Velasco-Paul. So we'd like to see you at those. Registration is now open, and we'll be sending you guys a link to these future events along with the recording of this webinar. Again, Dr. Khan, thank you very much for your presentation. It was great.
No problem, Kerry. Kerry, can you send me a picture of something? Or if you have, I don't know whether you can take a picture, right?
Yeah, I think I can. Let me get that and I'll send it to you. Thanks a lot.
No problem. Thank you. So I can disconnect now.